Hello grade 12s. We are busy with lesson 7 on our series in work, energy and power. And I'm glad to say after the previous video, which was a tough one, this one is very nice. It's mostly revision of grade 10 work, and we're going to look at the principle of conservation of mechanical energy. But as usual, before we do that, let's look into the problem that we had at the end of the previous video. The diagram below, not drawn to scale, shows a vehicle with a mass of 1,500 kilograms that moves from rest at point A at the bottom of the rough slope. Point B is at the top of the slope, vertically above the horizontal 200 meters. The total work done by force F that moves the vehicle for 90 seconds from point A to point B is 4,8 times 10 to the power of 6 joule. The speed of the vehicle when it reaches point B is 25 meters per second. Use the energy principles to calculate the total work done by the friction force on the vehicle. Now, if you have not completed this problem, I want to really urge you, for your own sake, stop right now and go and re-watch the previous video and do this problem. It's going to benefit you in the exam. As I always say, science is that's right, spectator sport. You have to get your hands dirty and you have to do this on your own. So let's continue with solving this problem. There I summarized all the information, and I'm going to look at the forces that's acting on the car first. So by now, you know what the typical 4 forces are. I have got my friction force, I've got gravitational force, I've got the tension in the rope, and I've got the normal force. And I know by now the normal force is not going to do any work, so I don't need to calculate that. I can immediately write that as 0. Okay, I'm going to use this equation where the work done by the non-conservative force is equal to the change in potential energy plus the change in kinetic energy. This is not the only way to solve this problem, but this is the theory that we've done in the previous video, and that's why I choose this method. So the first thing that I need to do is to identify my non-conservative forces, and what are they again? That is my frictional force as well as my applied force. So I can say the work done by the frictional force plus the work done by F, which is my applied force, is going to be equal to the change in kinetic energy plus the change in potential energy. So I don't have the work done by the frictional force. That's the amount that I need to calculate, but they did tell me the work done by the applied force was 4,8. There, that's that information, 4,8 times 10 to the power of 6. I also know my final velocity reaching the top is going to be 25, so I can plug that in. I know the mass of my vehicle is 1,500, so I've got a half times mass times final velocity squared. And I know I started from rest, so I have my initial velocity as 0, so I know the initial kinetic energy will also be 0. Okay, if I now look at my change in potential energy, my final potential energy was at a height of 200 meters above the ground, mgh, and my initial potential energy, because it's on the ground, is going to be 0. So I have all these numbers. I only have one unknown, so I can quickly calculate this plus that on my calculator minus the 4.8, and that will give me the work done by the frictional force as minus 1,39 times 10 to the power of 6. Do the negative sign make sense? Of course it does. Friction force is in the opposite direction of motion, so the angle between the friction force and the direction of motion is more than 90 degrees, and therefore I need to have a negative number for my work done. Now let's look at the conservation of mechanical energy, and you have done this in grade 10, so this is mostly revision. The principle for the conservation of mechanical energy, the total mechanical energy, that's the sum of the gravitational potential energy and the kinetic energy in an isolated system, remains constant. And I think the big question that you have here that you didn't have in grade 10 is this whole issue on what exactly is an isolated system. Well, you've dealt with isolated systems in momentum as well, conservation of momentum. A system is isolated when the resultant force or the net external force acting on the system is 0. So I can summarize this whole principle of conservation with the following equations. The first equation is my mechanical energy is equal to the sum of my kinetic energy and potential energy. Kinetic energy is a half mv squared. Potential energy is mgh. And this is true when the resultant force acting on the system is zero. When there is no resultant force acting on the system, then I can say, the mechanical energy is always this, but the principle for the conservation of energy, where I have the mechanical energy before a certain situation is equal to the mechanical energy a bit later, that is only true when I don't have any resultant force acting on the system. Now let's quickly look at an example. I did not really write the sum very nicely, but just to give you an idea, I have a pendulum that is dropped from zero, and I want to calculate its velocity just before it's hard, if it's just on the ground. This one is it's not touching the ground, it's just sliding past the ground. Okay, that's my scenario. I stated earlier this pendulum is dropped from zero. What do I mean by that? I just actually meant it's dropped from zero velocity. So velocity is 0 meters per second. It's not dropped from zero height. It's got a height of 1,2 meters per second. Height meters per second. No. It's got a height of 1,2 meters. Sorry for that. I sometimes get my words mixed up. And if I confuse you, let me know. And then I'll clear up the confusion. Anyway, let's continue. So I want to use my principle for conservation of mechanical energy. So I'm going to say the mechanical energy at the top. That is the mechanical energy for this pendulum right here, which is equal to the kinetic energy of the pendulum plus the potential energy right here, is going to be equal to the mechanical energy at the bottom, which is the kinetic energy at the bottom plus the mechanical energy, plus the potential energy at the bottom. Okay. So if I write this out, that is kinetic energy at the bottom, kinetic energy, I want to use kinetic energy at the top. I used B for beginning and A for after, but actually it should be bottom and top. Okay, forgive me for this one. Okay, so this should be kinetic energy at the top plus the potential energy at the top is equal to the kinetic energy at the bottom plus the potential energy at the bottom. Okay, so we fill in that values. I just told you I dropped this with a velocity of 0, so I know velocity here is 0, which means my kinetic energy at the top is going to be 0. My potential energy at the top is mass times height times gravitational acceleration, mass times gravitational acceleration times the height, and that is going to be equal to my mechanical energy at the bottom, which is the sum of my kinetic energy plus my potential energy. My height at the bottom is 0, and that is why my potential energy is 0. Do you see I actually don't need the mass of this pendulum? Why not? Because if you look at these terms or this equation, ignore the two zeros, adding the two zeros, can you see I can actually divide both sides by m? You see? Because it appears on both sides of the equation. So I have 9,8 times 1.2 is that just equal to a half v squared. So if I take 9.8, well, if I take both sides of the equation, divide both sides by m, then I take 9,8 times 1,2, times that by 2 to get rid of this half, and take the square root of that, I will get my velocity as 4.85. And that's it, just a little bit of revision of the grade 10 work. You have done this in grade 10. And therefore, as a little bit of a breather, I got this problem mostly from an old grade 10 paper. A steel ball of mass 5 kg is rolling over a frictionless surface, as shown below. When the ball reaches point A, it has a mechanical energy of 250 joule. Now this sketch is not drawn to scale, so you cannot assume that A and C is on the same height. It's not drawn to scale. You need to calculate the speed of the ball as at the instant it reaches point C, which you do know is 5 meters above the ground. Now see if you can solve this problem, and as always the solution to this problem will be in the next video. We're almost done. One to go. Good luck.